Um, what I'm going to talk about tonight is one of those things. But there's a quote that I like. There's a quote that I like very much. It comes from a famous intellectual by the name of Sherlock Holmes. And it says, when you have eliminated all that is impossible, which, by the way, sometimes takes 5 years, when you have eliminated all that is impossible, whatever remains must be the truth, no matter how improbable. The thing I'm going to tell you tonight is one of those things which seems nutty, it seems wildly improbable, but it wasn't just something that some of us, I wasn't alone in saying this, that some of us just said, oh, one day, maybe the world is a hologram. That's not the way it happened. The way it happened was exactly this way. When you eliminate everything that's impossible, whatever is left over must be the truth. So let me tell you a little bit about where we're going. Good. Okay. What is this thing which Sherlock Holmes might have eventually concluded after trying everything else? And the answer is that in a certain sense, in a certain peculiar sense, the world is a hologram. Now, not everybody knows what a hologram is here. You know, you've all seen these pictures which look three-dimensional. They're made out of a film, which is a flat piece of film. Nevertheless, they look fully three-dimensional. I'll tell you eventually what a hologram is. But the idea that the world is a hologram is a wild idea, or at least a seemingly wild idea. It all began with thinking about black holes. Black holes are those objects, in some sense, the most exotic objects in the universe. They're dense, they're heavy, they're dangerous, but they're also ubiquitous. The universe is filled with them. And not only that, almost all of the information, now we'll come to what information means, but almost all of the bits of information in the universe, by a vast majority, exist in black holes. So in a certain sense, although they may be very, very exotic, they're almost everything, at least almost all of the information in the universe. So I should begin by telling you or giving you a picture of what a black hole is. Now, I assume that I'm not talking to physicists. For those people who are physicists, you know what a black hole is. But for those who are not, I'll try to give you a picture. And the picture is an analogy. All analogies are defective. And I get some very funny emails from people who read my analogy somewheres and pulled out completely the wrong thing out of it. I hope you won't, but I can't protect myself against it. But let me give you my picture, a very simple picture that I actually learned from a famous Canadian physicist named Bill Unruh. But here's the picture of what a black hole is. Begin by imagining a shallow lake. It's an infinite lake. It goes on and on and on forever in two directions. But it's only about a foot or a foot and a half deep. It's not very deep. And fish live in it. Fish swim around. Now, these fish have a rule. Now, let's go to the -first law of physics. Why is it the -first law of physics? Well, the first law of physics, there are at least two first laws of physics already. One of them is in thermodynamics, the other is Newton's. So I didn't want to call this the first law of physics. It's more important and deeper than either of those two first laws of physics. Next, what is entropy? You've all heard the word entropy, and you probably heard that entropy has to do with confusion, and entropy has to do with chaos, and entropy has to do with the world coming to an end because everybody gets too confused to tie their shoelaces or whatever. But just like the bathtub where the number of drops of water is proportional to the volume, the natural expectation would be that the number of bits of information that it takes to build a black hole of a certain size would be proportional to the number of cubic meters or number of cubic kilometers or whatever it is, the volume. That is not what Bekenstein found. What Bekenstein found was that the number of hidden bits of information in the black hole is equal to the area of the horizon measured in a unit called the Planck unit. So that was the first surprising thing. The other surprising thing, well, it wasn't surprising at that time, at that point, but it might surprise you, that the size of one of these little bits, in other words, the area occupied by one of these little bits, right, is very, very small. 1 Planck area. Planck does not mean a board. It's the name of the famous physicist Planck, who has a constant named after him called h. G here is Newton's gravitational constant, and c is the speed of light. And if you work it out, it's 10 to the minus 66th square centimeters. It would take about 1,000 trillion of these little Planck areas to wrap a proton. To wrap the surface of a proton. So this is a very, very small unit, but nevertheless, it's a discrete little unit. And this is what Bekenstein calculated from the combination of quantum mechanics and properties of black holes. On the other hand, when Alice falls into the black hole and falls behind the horizon, as far as Bob is concerned, her bits have disappeared from the world. So in effect, for all practical purposes, for all physics purposes, Bob sees a world in which information is erased. Can this be right? This was Hawking's central point in 1976. When he created something that came to be known as the information paradox. It was an extremely deep observation. It was a very important observation. It is not important that Hawking didn't get the right answer. He asked the right question, and this became a central debate, a central question that took basically 20 or 25 years to resolve. We now know the answer, and we'll come to it. The answer is that bits of information never are lost, but nevertheless, the things that came out of the question is so deep that one can hardly say that it was Hawking's mistake. It was one of the deep observations about physics that led to great things. Okay, to make things even more confusing, and this was another discovery of Hawking's, an earlier discovery of Hawking's, black holes evaporate. They disappear. It's as if the box that you hid some information in, after a while, disappears. Little pieces of it break off and disappear into the atmosphere. And if I were to just draw or to use my extremely crude computer skills to try to make a movie of a black hole evaporating, what does it evaporate? It evaporates photons, light, gravitons, other kinds of particles. And as it evaporates, it loses energy, and in the process of losing energy, it shrinks. How that evaporation takes place is not so important. Basically, anything evaporates. Everything evaporates if you give enough time. And it eventually shrinks down to a very tiny black hole, and then it's gone. But when it's gone, where is Alice? Or more to the point, where are Alice's bits? Where are the bits of information that the minus first law of physics says can never disappear. The black hole is gone. Alice's bits could not have gotten out from behind the horizon. Why not? Because to get out from behind the horizon, they would have had to exceed the speed of light, just like the fish would have to exceed the speed of sound. And so we have a real dilemma. We have a conflict of principle. On the one hand, black holes seem to erase information. On the other hand, the most basic law of physics that I know says that information is never erased. It is the volume. That is not what Bekenstein found. What Bekenstein found was that the number of hidden bits of information in the black hole is equal to the area of the horizon measured in a unit called the Planck unit. So that was the first surprising thing. The other surprising thing, well, it wasn't surprising at that point, but it might surprise you, that the size of one of these little bits, in other words, the area occupied by one of these little bits, is very, very small. 1 Planck area. Planck does not mean a board. It's the name of the famous physicist Planck, who has a constant named after him called h. G here is Newton's gravitational constant, and c is the speed of light. And if you work it out, it's 10 to the minus 66 square centimeters. It would take about 1,000 trillion of these little Planck areas to wrap a proton, to wrap the surface of a proton. So this is a very, very small unit, but nevertheless, it's a discrete little unit. And this is what Bekenstein calculated from the combination of quantum mechanics and properties of black holes. This was interesting. Now, you could ask about a bathtub full of water. If a bathtub full of water has an entropy, it means it has hidden information. What is that hidden information? Well, we know now, today. It was not known, incidentally, around 1900. It was not known for certain that it was atoms, the motion of atoms and the positions of atoms, which made up the entropy of a bathtub full of water. In fact, it was Einstein who nailed that concept in place ultimately. But you could ask the same question about the black hole. If the black hole has entropy, it means there are hidden tiny microscopic degrees of freedom on the horizon, which we don't know about, which are somehow making up that entropy. We're sort of in the same situation as just before Einstein, when it was known that fluids and gases and materials had entropy, but it wasn't known for sure what the degrees of freedom, the little objects which constituted the hidden information. We're kind of in that situation. There are examples, theories, mathematical constructions. One of them is in string theory, and I'll just tell you very, very briefly what, according to string theory, the entropy of a Schwarzschild black hole is. I forget Schwarzschild, what a black hole is. String theory is a theory where elementary particles are little tiny pieces of string, little loops of string. A single elementary particle is the smallest possible loop of string, and it looks about like that, except a zillion times smaller. Now, you can take that little bit of string and you can heat it up. You can, how do you put more energy into it? You could put it into a frying pan and let it hop around, but that won't work very well. You collide other particles with it. You collide other particles with it. You smash it together with other particles, and the result is to add energy to it, and adding energy to it makes it vibrate and makes it get spread all over the place, just like a wildly excited rubber band oscillating all over the place. It gets tangled and it gets bigger. So you shake them one way or another and you increase their energy and you increase their size. You add even more energy and they get more complicated. Eventually, if you add enough energy, and remember that energy is mass, if you add enough energy, you'll get a great big, huge tangle of string. Does this tangle of string have entropy? Of course it does. If you're not smart enough or small enough or capable of following every little turn of the string, and you simply say that's hidden from you because it's too small and too numerous, you would say this complicated ball of string has entropy. It's a string tangle. Now this is not yet a black hole. On top of that, there's gravity. Gravity pulls it together. If you collect enough string with enough energy, eventually gravity will pull it together into a black hole. So what is left over after it forms a black hole? Something which looks metaphorically sort of like this. Little bits of string still hanging out of the horizon, and it's those little bits of string in string theory which constitute or comprise the degrees of freedom which carry the entropy. But I'm not here to sell you string theory. Whatever the entropy of black holes is, it's something that's very microscopic, too small to see, very numerous, very chaotic, and I also should add, in a constant state of agitated motion. And expansion. Well, this is exactly the way the universe that we know works. It is expanding. It's expanding with the same pattern of acceleration as if it were being fed new space, as if space were constantly being replenished, therefore being pushed apart, and it has a horizon. Each person has their own private horizon, namely the region around them which is moving away from them with slower than the speed of light. That region they can see, what's beyond it they can't see. So it looks something like this. Here's Bob at the center, and at some distance out, there's a point of no return, and if Alice crosses that point of no return, she's, as far as Bob is concerned, out of this world. Simply out of communication, never to communicate again. She's gone. There's a puzzling thing. It looks like there's a region of the world, maybe most of the world, which is out beyond all possible observation. What do we actually know about it? In fact, we know a good deal about it from observation. We know that the universe is at least 1,000 times larger in volume than the region that we can ever see. Ever see means within the horizon, within our horizon. The universe is at least 1,000 times bigger in volume than the horizon region. So there's stuff out there. That stuff is simply beyond observational science, period. Or maybe not. But at least in a simple sense, in the same sense that you can't see what's behind the horizon of a black hole, that stuff is out beyond the ken of any known method of observation. What is the meaning? I mean, this raises deep, both philosophical questions, scientific questions, puzzling questions that really do bother all people who think about this. What is the meaning of all the stuff out there, the scientific meaning of all the stuff out there, if it can never be detected? How can we ever hope to confirm it by real observation? What is the proper description of a world that is bigger than the cosmic horizon? These are all the same question, of course. But finally, is our cosmic horizon, the one surrounding us, is it a two-dimensional scrambled hologram of all that lies beyond it? These are questions which are deep, profound questions, and the only thing, I am not going to answer them, the only thing I can say now is we are all wrestling with them, and they're big questions, and they're hard questions. That's the physicist, incidentally. That's the universe. So I hope I've given you some flavor for the kinds of questions which we ask. But I want to convey something to you, that it's an extraordinarily remarkable fact. It's not a fact about me, it's a fact about the way human beings think, the way human beings, their cognitive abilities, that when you think about it for a moment, you know, a small, relatively small band of hairless apes has been able to deduce all of this, has been able to deduce such strange and totally unintuitive, very, very foreign ideas, very, very abstract ideas about the universe as peculiar and as unintuitive as the world is a hologram. I thank you.
Would Albert Einstein plead for a vision that exhibits 1. Childlike curiosity and 2. Exhibits the symmetry in nature, and 3. Is the culmination of a child's visual thinking, whose audiometric analog is, unequivocally, the prelude to also Sprach Zarathustra, and is in fact the uncontestable physical theory of e pluribus unum. Would Albert Einstein express himself with great passion on the question of the making of a motion picture for children worldwide?
These are questions which are deep, profound questions, and the only thing, I am not going to answer them, the only thing I can say now is we are all wrestling with them, and they're big questions, and they're hard questions. That's the physicist, incidentally. That's the universe. So I hope I've given you some flavor for the kinds of questions which we ask. But I want to convey something to you, that it's an extraordinarily remarkable fact. It's not a fact about me, it's a fact about the way human beings think, the way human beings, their cognitive abilities, that when you think about it for a moment, you know, a small, relatively small band of hairless apes has been able to deduce all of this, has been able to deduce such strange and totally unintuitive, very, very foreign ideas, very, very abstract ideas about the universe as peculiar and as unintuitive as the world is a hologram. I thank you.